So, what's the real difference between Java code that just works and a truly great, resilient system? The kind that can take a massive amount of traffic and not even flinch? It's not just about knowing the syntax. It's about understanding the entire life of a request from start to finish. So, let's do that. Let's follow that journey together. I mean, really think about it. You're on a website, you find something you want, and you click Buy. That one simple click, it unleashes this whole chain reaction inside the application. It's not just one thing happening. So how does a big application juggle your request with maybe thousands of others, all at the same time, without completely breaking a sweat? To figure that out, let's zoom in and follow one single brave little request on its entire adventure. Think of it like a package zipping through one of those giant, high-tech Amazon warehouses. It gets checked in, sorted, processed, and sent on its way. This is its story. Okay, our request has just hit the front door, but here's the thing. It's not alone, not even close. There are thousands of other requests showing up at the exact same moment. So the very first challenge is just, how do you greet all of them without the whole system falling over? This is the world of concurrency. So how does it manage all that traffic? Well, the old way was something called blocking I/O, one thread for every connection. Imagine a popular restaurant having to hire a separate waiter for every single person who walks in the door. It just doesn't work. Modern Java apps use non-blocking I/O, or NIO. Here, one thread is like a super efficient mitra D. It can handle tons of connections at once, and it only pays attention to a connection when it actually has something to say, like data that's ready to be processed. It's a total game changer for scale. Right, so once the request gets in the door, it needs someone to actually do the work. Now, creating a new worker or a thread for every single request is super slow and really wasteful. The answer? A thread pool. This is basically like having a team of chefs in the kitchen, already in their uniforms, ready to cook the moment an order ticket comes in. No delay. The app just borrows a ready-to-go thread from the pool. And Java gives us this incredible set of tools to manage all this. The executor service is kind of like the head chef who manages that team of workers. A blocking queue is a safe way to pass tasks from one worker to another, like a conveyor belt. A concurrent hash map is perfect for things like a shared cache that lots of threads need to read and write to safely. But the real magic for modern apps comes from tying all this work together without just sitting around and waiting. And this is a complete future task. It looks simple, but it is so powerful. It lets you build this beautiful pipeline of work. You can say, go fetch some data, then when that's done, transform it, and then when that's done, save the result. The key here is that it does all this without blocking a thread while it's waiting for each step. This is the secret sauce to making apps feel incredibly fast and responsive. All right, our request is in the door. It's been assigned a worker from the pool. Now we get to the heart of it all. It's time to actually do the work, to process the data. So let's imagine a really common business task. You've got this huge list of customer orders, and your boss wants to know the total revenue, but only from the orders that have been completed. Sounds simple enough, but doing it fast and clean is what matters. And this right here is the modern Java way of doing it. It's so cool. Instead of some clunky old for loop with a bunch of if statements, you use the Streams API. You can literally read it like a sentence. Take the orders, create a stream, filter out everything except the completed ones, then map each order to just its dollar amount and sum them all up. It's clean, it's readable, and it's incredibly efficient. But hold on. As we're doing all this streaming and filtering, we're creating all these little temporary objects behind the scenes. If those just piled up forever, the application would run out of memory and crash. So, who's the cleanup crew? Well, meet the unsung hero of the Java virtual machine, the garbage collector, or GC. You can think of it as this automatic janitor that's constantly sweeping through the application's memory. It finds all the objects that nobody is using anymore and clears them out, reclaiming that space. It's what keeps your application from drowning in its own trash. Now, the JVM's memory, which we call the heap, is actually pretty smart. It's divided into sections. New objects get created in the young generation, and most of them are short-lived, so they get cleaned up really fast. But objects that stick around for a while, like user sessions or cached data, get promoted to the old generation. The whole goal for a developer is to tune this process so that the garbage collector can do its job without causing these annoying pauses that freeze the application for the user. Okay, our request is really moving along now, but let's be honest, the real world is a messy place. Networks fail, databases time out, users type in garbage. So now, our request has to run the gauntlet of real-world failures. How it survives this part is what makes a system truly robust. And let's start with the absolute cardinal sin of error handling. This little piece of code right here, an empty catch block. We call this swallowing an exception. It's like seeing a fire start and just quietly closing the door. You haven't solved the problem, you've just hidden it. And now it's a ticking time bomb waiting to cause some mysterious bug later on. Now, Java actually tries to help us think about errors in two different ways. You've got checked exceptions, which are for problems you can kind of anticipate, like a file not being there. The compiler actually forces you to handle these. Then you have unchecked exceptions. These are usually just bugs in your code, like a null pointer exception. They signal that something is fundamentally wrong and needs to be fixed. So, here's a pro-level tip. When you do catch an error, don't just pass it on. Wrap it. Add context to it. Instead of a generic error, you can throw a new one that says, hey, there was an error processing order number 12345. That one little piece of information can be the difference between a 5-hour debugging nightmare and a 5-minute fix. And finally, what about cleanup? Let's say you open a connection to a database, and then an error happens. You have to make sure that connection gets closed, no matter what. That's where this beautiful feature, Try with Resources, comes in. It's a guarantee. It automatically ensures that your resources are closed properly, even if everything goes wrong. It makes your code so much safer. So, our request has made it. It navigated the traffic jam at the front door, it got processed efficiently, and it survived the gauntlet of potential failures. Its journey is complete. So, after seeing all that, what are the big takeaways for building systems that can do this millions of times a day? Well, it really boils down to a few key principles. First, you have to be deliberate about how you handle concurrency. Second, process your data smartly, using modern tools like streams, but always keep an eye on memory. Third, you have to plan for failure. Don't hide from it. Add context, clean up after yourself, and fail gracefully. And finally, know your tools. Using the right tool for the job, like the right kind of map or list, can make a world of difference. So we followed this one request and uncovered the advanced patterns that power the biggest, most performant applications out there. Things like concurrency, smart memory management, and robust error handling, they aren't just academic ideas. They're the absolute foundation of great software. The tools are here, they're proven. The only question left is, what are you